Welcome to the Deep Dive. We take cutting-edge research, boil it down, and give you those critical insights you need fast. Today, we're getting into something pretty fascinating, geometric deep learning. It's really changing the game in AI. I mean, you've seen AI master go, create stunning art, drive cars. Most of that is powered by deep learning, right?
That's right. But, what often gets missed is that standard deep learning really shines on data that's, well, neatly organized. Think pixels in an image grid or words in a sentence.
Right, sequential or grid-like.
Exactly.
Yeah.
But so many real-world problems just don't fit that mold. How do you handle, say, a social network or the 3D structure of a molecule or even just a complex shape? That data isn't on a nice, clean grid.
And that's where geometric deep learning comes in.
Precisely. GDL provides the tools to actually analyze these complex, non-Euclidean data types. It's a whole different way of thinking about structure.
Okay, so our mission today is to really unpack the why behind this. Not just what it does, but the core ideas driving it. We want to give you that shortcut to understanding. We'll dig into some fundamental math concepts, maybe uncover some surprising connections you might not expect. The goal is to give you that solid foundation quickly.
Yeah, and to do that, we're leaning on some really interesting sources, cutting-edge research papers, and very thorough course notes from experts at the University of Oxford. They offer this unique mathematical perspective on it all.
Great. So let's start maybe at the beginning. AI, the term goes way back, John McCarthy, 1956. But deep learning, what exactly makes it deep, and how does it fit into machine learning overall?
Well, the deep part is actually quite literal. Deep learning evolved from early ideas way back, trying to mimic biological neurons, artificial neural networks. Deep just means these networks have many layers of these computational units, these neurons. Each layer performs a transformation on the data it receives from the layer before it.
Building up complexity layer by layer.
Exactly. And machine learning, broadly speaking, is the whole subfield of AI that develops the math, the methods for designing these systems, and crucially, optimizing them so they can learn patterns from data.
Okay, so if that's deep learning, how does adding geometric change the picture? You mentioned these non-Euclidean structures. What's the fundamental shift?
The absolute core idea is about building prior knowledge about the data's structure, especially its symmetries, directly into the network's design.
Symmetries, like knowing a cat is a cat even if the picture is rotated.
Precisely that. Traditional deep learning might need to see thousands of rotated cats to figure that out. GDL says, wait, we know rotation shouldn't change the catness. Let's build that understanding in from the start.
That sounds much more efficient.
It can be, yes. It provides what are called inductive biases, basically. Helpful assumptions that guide the learning process.
Interesting. Now, our sources connect this to something called the Erlangen program from Felix Klein back in the 19th century. That sounds foundational.
Oh, it really is. It's a fantastic analogy the sources draw. Klein's idea was to unify different types of geometry, Euclidean, projective, etc., by studying what properties remain invariant, what stays the same, under different sets of transformations, like rotations or translations.
Okay.
So GDL takes inspiration from that. It tries to understand and even unify different neural network architectures by looking at the symmetries and invariances they are designed to exploit. It's not just about learning patterns anymore. It's about understanding the underlying rules, the symmetries that govern those patterns.
Wow, okay. That's a powerful way to frame it. It's like moving from just observing phenomena to understanding the physical laws behind them.
That's a great way to put it. It's a deeper level of understanding.
So if symmetry is so central, how do we actually, formalize it mathematically? It feels a bit abstract.
We use a concept from abstract algebra called a group. A group is essentially a set of elements like transformations combined with an operation, like applying one transformation after another, that follows specific rules.
Rules like?
Rules like associativity. It doesn't matter how you group operations. There has to be an identity element, like doing nothing or rotating by 0 degrees. And every element must have an inverse, an operation that undoes it, like rotating back.
Okay, can you give an example?
Sure, think about a square. The set of rotations that leave it looking the same, 0, 90, 180, 270 degrees, forms a group under composition. Rotate 90 degrees, then rotate 180 degrees. That's the same as just rotating 270 degrees from the start. It all fits together neatly.
And that structure captures the symmetry.
Exactly. It's the mathematical language of symmetry. Another example is the symmetric group, which describes all the ways you can permute or reorder a set of n items.
I can see how this applies directly to deep learning then. You mentioned translation and variance for images.
Right. Shifting an object in an image is a transformation. The fact that its classification shouldn't change means the classifier should be invariant under that translation group.
Or rotating a molecule in chemistry.
Exactly. The molecule's energy or properties shouldn't depend on its orientation in space, so the model predicting those properties needs to respect rotational symmetry. These symmetries provide those crucial inductive biases we talked about, making learning much more data efficient.
It's amazing how fundamental this idea is. Our sources even quote physicists like Emmy Noether and Philip Anderson.
Yeah, Noether's theorem is profound connecting symmetries directly to conservation laws in physics. And Anderson's quote, "Physics is the study of symmetry." Maybe a slight overstatement, but it captures how central symmetry is to understanding the fundamental laws of nature. GDL is trying to bring that power into AI.
Okay, so we have these groups describing symmetries. Now, the sources make an important distinction between G-invariant and G-equivariant functions. What's the difference there?
It's a key distinction. A G-invariant function means the output stays exactly the same when you apply a group transformation to the input.
Like the face recognition example.
Right.
Rotate the Mona Lisa, it still says Mona Lisa.
Perfect example. The output, the label Mona Lisa, is invariant rotation. It effectively collapses all rotated versions down to one single output.
Okay, and equivariant.
A G-equivariant function means the output transforms in a predictable way when the input is transformed. So if you rotate the input image of a face, an equivariant system might output the locations of facial features, but those locations would be correspondingly rotated.
Ah, so the output changes, but it changes with the input transformation.
Exactly. The relationship, the structure is preserved. Equivariance allows networks to learn richer, structured representations that track how things change rather than just collapsing them down. Both invariance and equivariance are crucial tools in the GDL toolkit.
Fascinating stuff. Okay, so we've covered symmetry and groups. Let's shift gears a bit and talk about the shape of data itself. This brings us to topology and manifolds. The sources use this phrase rubber sheet geometry for topology. What's that about?
Yeah, topology is a branch of math that studies properties of shapes that are preserved under continuous deformation, stretching, bending, squishing, basically anything you can do without tearing the object or gluing parts together.
Like stretching a rubber sheet.
Precisely. So from a topological viewpoint, a coffee mug and a donut are actually the same. Because you can continuously deform one into the other without tearing, they both have one hole.
Okay, that's weird, but I think I get it. It's about fundamental properties like connectivity, number of holes, things that don't change when you just bend the shape.
Exactly. It's more abstract than standard geometry, which cares about angles and distances. Topology introduces this notion of closeness or neighborhood without needing precise measurements. It defines which points are near each other through things called open sets.
And this leads to manifolds, spaces that look flat up close but can be curved overall.
That's the idea. A manifold is a topological space where, if you zoom in close enough on any point, the neighborhood around that point looks like standard Euclidean space, like flat Rn space.
Like the surface of the Earth. Locally flat, globally a sphere.
Classic example. Or space-time. In Einstein's theory of relativity, it's a four-dimensional manifold that's curved by mass and energy. Manifolds give us the math to handle data that doesn't live in a simple flat space, but on some kind of curved surface or structure.
And on these curved spaces, the shortest path isn't necessarily a straight line, right? You mentioned geodesics.
Correct. A geodesic is the generalization of a straight line to a curved manifold. It's the shortest path along the surface between 2 points. On a sphere, that's an arc of a great circle.
So if our data lives on, say, a sphere or some other curved manifold, how do GDL models actually work with it? Standard calculus assumes flat space, doesn't it?
It does. And that's where tools specific to manifolds come in. One key idea is the tangent space. At any point on the manifold, you can imagine a flat plane that just touches the manifold at that point. That's the tangent space. It's a standard vector space like Rn that provides a local flat approximation of the manifold right at that point.
Okay, like a flat map projection of a tiny region of the Earth.
Kind of, yeah. And then you have mappings like the exponential map and logarithmic map. The log map takes points on the manifold near our chosen point and maps them onto the flat tangent space. The exponential map does the reverse. It takes vectors in the flat tangent space and maps them back onto the curved manifold, typically by following geodesics.
So you can sort of do calculations in the familiar flat tangent space and then map the results back onto the curved reality.
That's the intuition. It allows us to adapt methods from standard deep learning to work on these curved domains while respecting their intrinsic geometry. For instance, you might learn representations in a flat tangent space and then use the exponential map to place them onto a specific manifold, like the Poincare ball, which is useful for hierarchical data.
And what about gauge transformations? That sounds complex.
It relates to choosing local coordinate systems. On a manifold, you often need coordinates, but the choice is arbitrary, like picking which way is north on your local map. A gauge transformation is just the mathematical rule for how things change when you switch from one valid local coordinate system to another.
Okay.
EDL aims for operations to be gauge equivariant. This means the results shouldn't depend on the arbitrary choice of local coordinates. The learned features should be intrinsic to the data's geometry, not an artifact of how we chose to measure it locally. It ensures robustness.
This all seems connected to the manifold hypothesis in machine learning. What exactly is that hypothesis?
It's a really influential idea, though often stated informally. It suggests that most real-world high-dimensional data, think images, sound waves, maybe even language embeddings, doesn't actually fill up the entire high-dimensional space it technically lives in.
It occupies only a small part of it.
A very small part, yeah. The hypothesis is that the data points actually lie on, or very close to, a much lower dimensional manifold that's embedded within that huge ambient space.
Can you give that face example again?
Sure. Think about all possible combinations of pixel values for, say, a 1,000 by 1,000 pixel image. That space is astronomically vast. But if you pick a random point in that space, you'll almost certainly get meaningless static, just noise. The actual images that look like human faces occupy a tiny, tiny fraction of that space. The manifold hypothesis says these valid face images form a relatively low-dimensional, possibly curved face manifold embedded within the high-dimensional pixel space.
And what's the practical impact of knowing or assuming that?
It's huge. If the data lies on a low-dimensional manifold, maybe we can learn more efficiently by focusing on that intrinsic structure. And it explains why simple linear interpolation often fails. If you take 2 points on a curved manifold, like two faces, and just draw a straight line between them in the high-dimensional space, that line will likely pass through regions off the manifold regions corresponding to blurry, unrealistic images.
Ah, but if you move along the manifold.
Right. If you traverse the manifold, following its curve perhaps along a geodesic, you can smoothly morph one face into another, passing only through other valid, realistic face images. This is crucial for things like generative models, creating new data, and understanding how features vary smoothly.
Okay, that's a really clear picture. Now let's switch gears again to another fundamental structure for GDL graphs. This seems central to graph neural networks, GNNs.
Absolutely central. Graph theory is arguably the mathematical heart of GNNs, and it's a key part of what we call discrete geometry. It deals with relationships, connections. Think back to the famous Königsberg Bridge problem Euler solved that was basically graph theory avant la lettre. Cities as nodes, bridges as edges.
So what are the basic graph concepts we need for this discussion? Nodes, edges.
Yep. You have nodes or vertices representing entities, people, molecules, web pages, whatever, and edges or links representing some kind of relationship or connection between them. Edges can be directed, A points to B, or undirected, A and B are linked.
And we represent this structure mathematically.
Often with an adjacency matrix. It's a matrix where the entry, I, J, tells you there's an edge between node I and node J. From there, we can talk about properties like connectivity. Can you get from any node to any other? Node degree, how many connections a node has. Shortest path distance between nodes, the graph geodesic, and so on.
And graphs can model all sorts of data, right? Not just social networks.
Oh, definitely. You have point clouds, which are common in 3D vision, basically just nodes representing points in space, maybe initially without edges. Then you have geometric graphs, where nodes do have spatial coordinates, and edges might represent proximity, like atoms in a molecule connected by bonds. And meshes, used heavily in computer graphics, which have nodes, edges, and also faces to represent surfaces like the Stanford Bunny model.
What about properties of the connections themselves? I think our sources mention homophily.
Right. Homophily, it's the principle that birds of a feather flock together. In graph terms, it means connected nodes tend to be similar or belong to the same class. Like in a citation network, papers often cite other papers in the same field.
And the opposite would be heterophily, where connections are more likely between different types.
Exactly. Some networks exhibit homophily, others heterophily. Understanding which one dominates is important for designing effective GNNs, as many standard GNNs implicitly work better with homophily.
How does the group theory we discussed earlier about symmetry relate to graphs? There was something about node labels being arbitrary.
Yes, permutation invariance. This is absolutely crucial for graphs. unlike pixels in an image grid, which have a fixed order, top left, next pixel, etc. The nodes in a graph usually don't have an intrinsic order. You could list them alphabetically or by degree, or randomly, the underlying graph structure is the same.
So the computation shouldn't depend on how we happen to list the nodes.
Precisely. GNN operations, especially the aggregation steps where a node gathers information from its neighbors, must be invariant to the order of those neighbors. That's why functions like sum, mean, or max are used. They give the same result regardless of the input order. They are permutation invariant aggregators.
Okay. And that ties into things like graph isomorphism, checking if two graphs are structurally the same, even if nodes are labeled differently.
Exactly. The Weisfeiler-Lehmann test is a classic algorithm related to this, and understanding the expressive power of GNNs is often linked to their ability to distinguish non-isomorphic graphs.
Now, the graph Laplacian came up again. We talked about the continuous version on manifolds. How does it work on a discrete graph?
It's analogous. The graph Laplacian is a matrix derived from the graph's adjacency matrix and node degrees. It acts as a difference operator on signals defined over the graph nodes. A key property is its quadratic form, which measures the smoothness of a signal across the graph.
Smoothness meaning neighboring nodes have similar values.
Yes. If a signal, like node features, varies smoothly across connected nodes, the Laplacian quadratic form will be small. If it jumps around wildly between neighbors, the value will be large. And just like the continuous Laplacian, its eigenvalues and eigenvectors are really important.
Eigenvalues as graph frequencies.
That's the intuition. Low eigenvalues correspond to smooth, slowly varying patterns across the graph, low frequency, while high eigenvalues correspond to highly oscillatory patterns, high frequency. The eigenvectors form a basis, like a graph Fourier basis, allowing us to analyze signals on the graph in terms of these frequencies.
So putting this together, how do graph neural networks actually learn using these graph structures and the Laplacian ideas? What's the mechanism?
The dominant paradigm is message passing. It's an iterative process where nodes update their representations, their features, based on information from their local neighborhood.
How does that work step by step?
Typically, in each layer, every node does three things. First, it might generate messages based on its own features and the features of its direct neighbors. Second, it aggregates all the incoming messages from its neighbors. This is where permutation invariance is key, using functions like sum or mean. Third, it updates its own feature vector using its previous feature vector and the aggregated message.
So information propagates locally across the graph, layer by layer.
Exactly. It's like nodes having structured conversations with their neighbors, refining their understanding over multiple rounds or layers. The graph structure dictates who talks to whom.
That's really neat. And you mentioned earlier that even things like attention mechanisms and transformers can be seen through this lens.
Yeah, it's a fascinating connection. You can view the attention mechanism, where every input token calculates how much attention to pay to every other token, as implicitly learning a fully connected, weighted graph structure on the fly. The GDL perspective helps unify these seemingly different architectures.
So ultimately, how does graph theory really empower GDL and AI? What problems can it solve that were hard before?
It lets AI directly model relational data. Instead of treating data points in isolation, GNNs explicitly use the connections, the graph structure, as a geometric prior to guide how information flows and how representations are learned.
Which leads to breakthroughs in
Social network analysis, understanding influence or communities, drug discovery and bioinformatics, predicting protein functions or molecular interactions based on their structure, recommendation systems suggesting items based on user-item interaction graphs. Basically, anywhere the relationships between data points are as important as the data points themselves.
What an amazing tour. We've gone from really abstract ideas like sets and symmetries.
Right, through the geometry of curved spaces, these manifolds.
And landed on the very concrete structure of graphs and how they let AI understand the connections.
It really shows how GDL is broadening AI's reach, allowing it to tackle these incredibly complex, structured data sets that are everywhere in the real world, far beyond simple grids.
It feels like understanding these mathematical underpinnings gives you a completely different perspective on what AI can do and where it might go next. It's not just pattern matching anymore.
Not at all. It's about building in an understanding of shape, symmetry, relationships, the fundamental geometry of the data. That makes the AI potentially much smarter, more robust, and more data efficient.
So as we wrap up, maybe a final thought for you, our listener. As AI keeps pushing forward, we're clearly moving beyond just finding patterns in flat data sets. We're starting to equip AI to understand the inherent shape and structure of information itself.
So consider this. What becomes possible when we truly embrace this geometric view? When we think of even complex, maybe seemingly chaotic data as potentially just points lying on some intricate curved surface in a higher dimension, just waiting for us to explore its geometry. How might that fundamentally change how we think about learning, knowledge, and maybe even intelligence itself?